Hi, Shishu. I guess you got the notification today.
Yes, it worked. I got it. Thank you.
Good.
Yes.
All right, Atul. Go ahead.
Sure. So, welcome all of you. Good afternoon. It's a great pleasure to introduce our next speaker, Dr. Nayandeep Baruah from Tezpur University. So, Nayandeep got his PhD from Tezpur, and then he was at Urbana-Champaign for a postdoctoral fellowship under Professor Pant, which was the same year when I entered for a PhD there. So we overlapped for that 1 year in 2006. And since then, I have been in touch with Nayandeep. So he works in partitions, Q series, combinatorics, and not many of you must be knowing that he remembers the digits of pi to really amazing number of places. I don't know how much is it, Nayandeep?
No, I'm trying to forget.
Okay.
So right now, I think more than 200 I can do it.
Oh, wow.
But in my peak days, I was almost 5,000. Yeah.
Wow.
But now I do not practice.
Okay. Okay. So today, Nayandeep will be talking on matching coefficients in the series expansions of certain Q products and their inverses. Over to you, Nayandeep.
Okay. Thank you, Atul, and Gaurav also for your kind invitation. So I will talk on matching coefficients, and that I will define what we call a matching coefficient. So I want to share my screen, but while sharing the screen, my video will go. Is it visible?
No.
Yes.
Hello?
Yeah. It is visible.
Is it just I'm writing the date?
Sure.
Yeah. All right. So we just recently we saw that the series expansion of certain Q products have interesting this matching coefficients with their inverses. As a definition, so I would say that suppose this is the series representation of a Q product, this one, and suppose I denote A prime n Qn. This is the series representation of the inverse of a Q product. Okay. So this is this is a Q product, say, and I said it like this. Then for some Q products, we have seen that these An and A prime n, they actually match in some subsequences. Okay. For example, in the abstract, you can see that if we consider that RQ denote the Rogers-Ramanujan continued fraction, where we do not consider Q1 over 5, that we do not consider. We only consider the Q product representation of RQ in the form, say Q5 infinity, then Q4, Q5 infinity, and Q2, Q5 sub infinity, then Q3, Q5 sub infinity. Then we saw that if I denote alpha and Qn, this is the series representation of 1 over r to the power 5q. And if I denote the coefficients by alpha prime n of this one, and then this alpha of 5n plus 3 is equal to minus alpha prime 5n plus 1, and alpha of 5n plus 4 is just minus alpha prime 5n plus 2. So therefore the coefficients alpha n and alpha prime n of 1 over r power 5q and r to the power 5q, they actually matches. For example, in this 5n plus 3 here for alpha, and here 5n plus 1, and there is a minus sign here, negative sign. Similarly, the others. And actually, we have seen many such Q products for different theta functions. Then the Q products arising from different continued fraction representations and modular equations. That means Q products arising from modular equations, etc. So this is a joint work which my research scholar Hirokjoti does. And so I want to speak on this. That means why such a nice representations actually, from where it comes. Okay. And there might be more such relations. That means relations among the coefficients of any of such Q products and their inverses. And first example I want to give is from some Q product identity that is arising from Jacobi's famous identity. Okay. So let me state that. For that, we have to define Ramanujan's general theta function f of AB. And so we define this Ramanujan's general theta function f of AB. So this is A of n and n plus 1 and B by 2 and n minus 1 by 2. So, and modulus of AB is less than 1. And this is from n equal to minus infinity to infinity. So this is Ramanujan's general theta function f of AB. And by Jacobi triple product identity, I can write this as minus A, AB infinity, minus B, AB infinity, and AB infinity, sub infinity. And where we, as customary, we define what? A Q infinity is just a Q product 1 minus A Q, says J, J equal to 0 to infinity. Okay. And for shorthand notations, we will use A1 Q infinity, A2 Q infinity, and AK, say Q sub infinity is A1, A2, and AK Q infinity. Okay. So these are the notations. And now there are three special cases of Ramanujan's theta functions. For example, if we choose A equal to minus Q and B equal to minus Q square, then this we denote by f of minus Q. And that is actually from Jacobi's triple product identity, we have QQ infinity. And we denote it by F1. And in general, we call F7 to denote QQ. For example, F1 is Q square, Q square, sub infinity, etc. Phi Q, and that is f of QQ. And this is by Jacobi's triple product identity, we have minus Q, Q square, and there are two terms like that because it is minus Q and minus Q, then Q square, infinity. And we have another Ramanujan's theta function, f of Q, Q cube. And that by Jacobi's triple product identity, and then simplifying, we can write this as Q square this, and Q square infinity. Now, using these definitions of phi and psi, we can transform the Jacobi's identity. The famous Jacobi's identity is 4th power of phi q is equal to 4th power of phi of minus q, and then 16q and psi to the power 4 q squared. Okay, so if we transcribe this into Q products, so we'll get that this is nothing but your minus q square infinity. This was squared. Here it was squared. So now fourth power. So it is 8. And there is a f2. F2 is q2 sub infinity. And so therefore it is f2 power 4. And on the right hand side, I will get just the q square power 8 and f2 4. And here I will get minus 16q. And because psi q is this one. So I will get this is, and this is psi q square. So it is f4 power 4 and divided by q square. So this is just a representation of Jacobi's identity. And from here, it actually follows that minus q square 8 and minus q square 8 is equal to, so so this is nothing but f4 is nothing but q2 so this is f4 and this is q2 q4 and sorry, q2 q4 and q2 q square and minus q2 q square. So therefore it is minus q2 q square, and we applied Euler's identity that 1 over q square is equal to minus q infinity. So this is the Euler's identity, which gives the partition analytic version of the partition theorem, his partition theorem, that number of partitions of n into distinct parts is equal to number of partitions into odd parts. So applying that, so one can easily check that this is nothing but 16q over q2 q4 8. All right. So therefore you see that if I take this as the q product, so this is the negative of, that means if I denote, so you can say that if say we define say an qn is say the coefficients of this q square 8, okay, and the inverse of that means the inverse of the q product, suppose they that has this power series, then we have what your an qn by the previous identity. So this is nothing but q square sub infinity power 8 and minus q square sub infinity power 8, and there is a minus sign on the right hand side also. So I have where I have here an minus qn, and that is equal to your 16 and a prime of n q to the power twice n plus 1. Okay, so here the limit 0 to infinity, and so it immediately follows that by equating the odd powers, that means coefficient of the odd powers of q, we have a of twice n plus 1 equal to, so there is a minus sign here, so minus 8 a prime of n. So you see that this is a result on matching coefficients. So we call that matching coefficients. So we took the product, we considered this product, okay, and if we take the inverses, then they are related by this. So this type of results we call the matching coefficients. Okay. So this is one simple example. But there are many other results of this type. Okay. And one result I want to mention, that 3 results actually. So those actually comes from the p-dissection of f of minus q, phi of q, and psi of q. So those comes from the p-dissections. So here, this one you see. Is it visible?
Yes.
Yes. So you see that this is the p-dissection of f of 1. Okay. f of 1. And here your p is actually strictly greater than 3. P is an odd prime, and that is strictly greater than 3. So we have this p-dissection. This was found by Kui and Gu, I think. Yeah, Kui and Gu in Advances in Applied Mathematics in, I think, 2009. Okay, something like that. So, and it follows from one of Ramanujan's identities in his notebooks. Okay. So, so this is a p-dissection of f1. Now you see the powers of here. So here we notice that this is f of minus q power p square, and here these are all powers of p. So these powers are the multiples of p. So here also there is a multiple of p, and that is actually p square. And here plus minus p minus 1 by 6, that is defined by this for p congruent to 1 mod 6, the first one, and p congruent to minus 1 mod 6 is the second one. And furthermore, when we consider k equal to minus from this to this one, and where k is not equal to that one, then we see that these powers of the sum, okay, this is never congruent to p square minus 1 by 24. That means the power of the factor of f of minus q power p square. So therefore, so what we did here is that we divide by this f of minus q, we divide by f of minus qp. Okay, so this may be very haphazard, but what we did, we divide this by what? F of minus qp, left hand side, and right hand side also we divide like that. So this is f of this one, divided by this. And here also it is divided by, you can say that f of p, we divide by f of p. So this is divided by f of p, which is same as f of minus q to the power p in notation. So we have that your f of 1 by f of p is equal to, we got minus 1 power plus minus p minus 1 over 6, and q power p square minus 1 over 24 we got. And this we got f of p square by f of p, and rest are like that. All multiples of this except the first one. That means there in the front there is a q power something. That means q power 3k square plus k by 2. But that is not congruent to p square minus 1 by 24. Okay? That means 3k square plus k by 2 is not equal to some multiple of p, pk plus this one, p square minus 1 by 24. So your 3k square plus k over 2, that is not equal to this one. Okay? Or this I can take n. All right. So therefore,
Yeah. Did you say that on the theta function on the extreme right, the exponents of that are multiples of p square? I mean, in the beginning.
Yeah, p square.
Why is that the case? 6k plus 1 is divisible by p.
Which one?
No, I see 3p square in the top, but there is also the 6k plus 1 times p. So is it divisible by p square? Or am I missing something? Those exponents on the theta function on the right.
Or this one?
No, on the very right.
This one?
Extremely.
Yeah.
Yes. Those exponents are divisible by p square, you said?
Not p square, p.
P, okay.
Those are divisible by p.
Okay.
Because there is a multiple of p, you see, everywhere there is a multiple of p. Okay. So you see that on the first term, we have got fp square over fp, and on the left I got f1 by fp, and in front q to the power p square minus 1 by 24, and there is in front it is always 3k square plus k by 2 power. So therefore, but this one is just inverse of this. Okay, so therefore we can find matching coefficients of f1 by fp. If we equate the coefficient of q power pn plus p square minus 1 by 24. So that is the theorem. You see, this is the theorem. This is the theorem, first theorem. Is it visible? So I denote gamma 1n by q square, then qp minus 1 and qp. Okay, so that is nothing but f1 by fp actually. So we have written in terms of only q products because your fp means qp, and that will be cancelled out. So only we are left out with this product. Okay. So if we take gamma 1 as this one and the inverse of that as gamma 1 prime, then you equate the coefficients of pn plus p square minus 1 by 24. So we equate these coefficients. So therefore we get that your gamma 1 of this one is equal to this one. I think I'm clear here, because on the right hand side, second product, this product, these are never equal to pn plus p square minus 1 by 24. So that will be left out actually. Okay. So that is our first theorem. That is our first general theorem, you can say. So that is the theorem gamma 1. Similarly, we take the second, this product, this p dissection of psi q. This is the p dissection of psi q, where psi q we have f2 square by f1. So in q product, I can write like this, f2 square by f1. So this is your p dissection, and here also because your k square plus k by 2 is not congruent to p square minus 1 by 8. Because if we take that equal, then we will get a contradiction actually. So we get a contradiction, and that has already been proved by Kui and Gu. Okay, so therefore we have psi q is this, and now here also you see that on the first term we have psi of q p square, So therefore you just divide both sides by psi q and psi qp. And the first term is just, you can say that this is the inverse of the original product, psi q by psi qp, but q is replaced by qp. Okay. So therefore we equate again the powers of q powers of pn plus p square minus 1 by 8. So therefore we get the that result. So this result we get. If we denote gamma sub 3 n as this q product, and the inverse is gamma 3 prime, then we have third theorem. And for the second theorem, we just apply for this one. That means the p dissection of phi q, and this has been stated by us in Proceedings of American Mathematical Society's journal on some results on 3 course. So we have used this p dissection, and this also was found by using Ramanujan's identity in his notebooks. Okay, so these are the 3 general matching results on matching coefficients. Okay. And then we saw that for F1, if we take p equal to 3, 5, 7, 11 small primes in the p dissection of F1, then we get some more results. That means these general results are already found, but we will get some specialized results on that. If we choose p equal to 3, 5, 7, 11 these dissections of the Euler product QQ sub infinity. So these are those special results. This one, for example, if I take 3, 3, that means delta of mkn we denote by f1 power k and fm power k. So if it is 3, 3, so we have what? Your F1 3 by F3 3. That's F1 power 3 by F3 power 3. So this is a Q product. And so we use the 3 dissection of F1 cube. So there is a 3 dissection of F1 cube. Okay. So, and using that, we actually found the first theorem. Similarly, squaring that 3 dissection, we can get another formula for power 6, F1 power 6 divided by F3 power 6. So similarly, if we take m equal to 5, that means F1 power k over F5 power k. That means F1, F5 form. Okay. So then we take squares, and then we get more results. So this one is that. Cubing it, we get 4th power, we get, etc. 8th power, we get. So there are more results like that. Similarly for 7, then 11. And for actually 13, it doesn't work. So we have seen that for 13, we are not getting that type of results, because while squaring, we do not get that these coefficients are left out with only those are equal. So that is not coming in 13, in case of 13 and higher powers. And similarly, if we take two products, for example, here if we define delta L M K as F1 power k, FL power k, etc. So if we choose say 2 3 1 here, 2 3 1 means F1 1, then F L equal to 2, F1 by F2, then M we take 3, so it is F3 by F6. So I think here I read F1 by F2, F3 by F6. Then also we get some matching coefficients. So for example, 3n plus 1. So we can see the pointer here, 3n plus 1, that is same as minus delta prime of n. Same is the case for 2 5 1. Okay. So we got several other results. So this one. So these are coming from special 3, 5, 7, and 11 dissections of Euler product F1 and the powers and the combination of two Euler products like that and their quotients. Then we have more results of another type. For example, we have that. We know that your psi q7, this has a two dissection. Two dissection of the form, say something like aq square and plus q of, interestingly, it is q psi q square and q psi q 14. And aq square can be written in terms of what? Phi and psi, but that is that there are 4 terms here, but we do not require this to get a result of matching coefficients. So we have this one. So therefore you put just q equal to minus q here. So we have this one, and this remains as aq square, and here it is psi q square and psi q power 14. And if we subtract, then we see that this is psi q 7 and minus psi minus q psi minus q7 is equal to twice q and psi q square and psi q 14. And from here, it actually follows that if we transcribe these two q products, then we see this as q square sub infinity, then q7 q14 sub infinity, then minus q square sub infinity, minus q7 q14 sub infinity, and that is equal to minus twice q, and we have here actually q square sub infinity and minus q14 sub infinity, but that I can write as by Euler's theorem into distinct parts and odd parts. So we have Q square, Q4 sub infinity, and Q14, Q28 sub infinity. So, and from here, it follows that if we consider this product, okay, so this is just negative of that. That means Q replaced by minus Q. And here it is just the inverse of that product where Q is replaced by Q square. So therefore, if we denote this by Bn, say, Bn Qn, and this is nothing but Bn of minus Qn, and here it is nothing but minus 2 B of B prime of n Q power twice n, and there is a Q in front, so therefore twice n plus 1. So you just equate the coefficients of Q power twice n plus 1, and we'll get that your B of twice n plus 1 is equal to minus B prime of n. So this is another result of a Q product which have matching coefficients with its inverse. And here, actually in these partition functions, minus Q squared and minus Q7, Q14 infinity. So this is the generating function for number of partitions of n into distinct parts, but there are two colors for the parts which are multiples of 7. Okay, so these results were already discussed. Those partition theoretic results were already discussed by Barnes, which actually follows from Ramanujan's modular equations. So actually, the earlier Q product, this Q product is equivalent to Ramanujan's modular equation of degree 7. So 1 minus alpha, 1 minus beta to the power 1 over 8 equal to 1. So this modular equation. So this is given by Ramanujan as well as many other mathematicians, and those were discussed by Barnes in his paper in Annals of Combinatorics in 2007, partition theoretic interpretations of certain modular equations of Schroeter, Russell, and Ramanujan. So this is one of those equations. So these are degree 7. And we see that there are more modular equations of this type of degrees 3, 5, then 11, 23. And we have seen that from each of them, a result of matching coefficients arise. Some results of matching coefficients arise. And not only one, if we cube it or square it sometimes, then we get more results on matching coefficients. Okay, so for example, if we cube this 7-degree modular equation, we get another result on matching coefficients. So that is written in our paper. Okay. So for example here, so here we know this one. So for example, these are all those results which are coming from Ramanujan's modular equations of Russell, Schroeter, and this Ramanujan. So those are of this form. Okay, that means we denote by zeta mk. So therefore, there are some results on zeta. So this is coming from degree 3. This is coming from degree 5. This is from 7 that I have just stated or proved, and this is coming from the cubing of by taking cube of the earlier results. Then this is 11, then this is 23, and there is a mixed modular equation of that Ramanujan, Schroeter, and Russell type, and that was proved by Barnes and myself in JCTA paper in 2007. Okay, and from there also we get a matching coefficient result, but in that case there are as many as 4 colors. That means the concerned function is this one. The corresponding function is this one. 3, 6, then Q5, Q10, this one, then Q15 and Q30 infinity. So this is our Q product. If we take this Q product and the inverse, the coefficients are given by theta n, say, and the inverse of that is given by theta prime n, then this is the result. And that is coming from a modular equation of degree, mixed degree actually, 1, 3, 5, 15 of Ramanujan, Russell, and or this is only found by Ramanujan. Okay. So this is one category that we have found results for matching coefficients. And in fact, there are more. There are more modular equations of Ramanujan which are not of those type, but still we can get some results. For example, from a degree 3 and 5 of this type, we can get another result. Okay. Just I want to mention the type of modular equations. So for equation like this: 1 beta cube, then 1 minus alpha power 1/8 minus beta cube alpha 1/8 equal to 1 in Ramanujan's notebooks, part 3 in Barnes series. So from here, we actually get the result, get a matching coefficient result. And the concerned Q product is here, cube over q square infinity. This is the Q product. If we consider this Q product and use this modular equation, or rather we transcribe this modular equation into Q products, and we see that actually we get a Q product identity which gives the required matching coefficients. For example, if I denote this coefficient of the power series by n mu, it is mu n twice n plus 1 is equal to mu sub 1 3 prime n. So this result. So from Ramanujan's modular equations, we transcribe these to Q products, and we see that this is the corresponding result for matching coefficients. So we found the other results, which are mu of mk, we define like this. So if k equal to 5, we get another Q product, which is coming from modular equation of degree 5. Okay. So for 3 and 5 we got here, and here also 3 and 5. And this is connected to Ramanujan's cubic modular equation. Sorry, cubic continued fraction. The Q series Q product representation of Ramanujan's cubic continued fraction. So we can transcribe this to Q product, and we have results for matching coefficients. So this. So I am not going into the details of the proofs, but it will naturally come and like that. But the most interesting the results on matching coefficients came from the Rogers-Ramanujan's functions ZQ and HQ. So we know that Ramanujan actually recorded 40 identities involving ZQ and HQ, and those were fully proved only in this century. And there are some new results on ZQ and HQ. And we checked whether the results on matching coefficients comes from those 40 identities and some new identities found by Yesselwood and Goog and so on. But we saw that only a few results came. For example, only for this one, which is stated in the abstract, this one, I think this one. These three results comes from some identities connecting ZQ and HQ. There are 40 identities of Ramanujan, but from others, we did not get. We have checked numerically, but we did not get. So the problem is that why we are not getting. So I'll tell you in a minute. So, for example, here you see that Ramanujan recorded for example, let me see here. This one, see. So let us denote lambda 9n qn by rq over rq power 16. rq over rq power 16. We notice that to prove Ramanujan's result, we need a relation between ZQ16HQ and plus Q power cube, Q cube, plus Q cube. So you notice this plus Q cube. And Ramanujan actually recorded this is minus Q cube. So he has a formula for minus Q cube. So when we check that when it is minus Q cube and we try to find the matching coefficient results, then we failed. That means it is obvious that if I denote this by the second term, this can be written as what? RQ over RQ 16 and minus Q cube. This one. Okay, so we can write like this, because we know that your RQ is nothing but HQ over ZQ. So most of the Ramanujan's results, either it is plus Q power something or minus Q power something. So whatever he has written, so we checked, and only for one relation we found a matching coefficient result, and for others we have seen that we must change something. That means here Ramanujan written minus Q cube, but we must need a relation of plus Q cube. So that was not there. That was not there in Ramanujan's list, as well as not there in the modular equations found by Sinai Robbins in his thesis, then Goog in his 3 or 4 papers, and Shuni Kang, and in Ramanujan's lost notebook by Barnt and Andrews. So we could not find those results. So therefore, we actually found this. This is a new result. So this is a new Rosas-Ramanujan, a new relation for ZQ and HQ. Similarly, to prove the other theorems, that running this one, all these. So we have to have some extra results, and those extra results we have. So all these 3 are new. So these 3 are new results on ZQ and HQ. So after finding these new results, we proved that theorem for this theorem. So if lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, lambda 7, lambda 8, all these are defined by this, then we have these many results. Okay. And this one I have stated in the abstract, and the first one I think I have stated in the abstract. So the rest are, I think, also the beautiful results connecting ZQ and HQ. And we know that there are analogous results for analogous functions as Rosas-Ramanujan functions. So there are Goldnisch-Gordon functions, which are defined by SQ and TQ, and there are many modular relations like ZQ and HQ for SQ and TQ also. So SQ and TQ also connected by modular relations, and those are found by first found by Wang. Many of them were found by Wang, then Chen and Huang, then Jia and Yao. They also found some new results. Then with my students Junali and Nipen, so we found more results between SQ and TQ. So we explored those results, whether we can find new results on matching coefficients for arising from those results. And we have found many, and we also proved one new theorem, so that our new matching coefficient result can be proved. So this is a new result involving SQ and TQ. So this is another new result. So using those, we found many results of matching coefficients. Those are arising from the relations of SQ and TQ. So we have stated in a theorem here. And for that, we have defined actually 9 coefficients, different type. And we can vary K because there are relations connecting this Ks. Okay. So we have this one. For example, rho 1, 1. So rho 1, 2. So K equal to 1 and K equal to 2 here. So those are connected. For example, similarly for 2, 3, and this is 2, 5, 2, 7, 2, 9. Similarly, 3, this is different K. This is 3, this is 5, this is 9. Okay. So we have found many results of this type. And there are Rogers-Ramanujan type functions given by Slater and whose Q product representation is given by this one. Okay. And that we denote by XQ, and this is by YQ. And there are modular relations for XQ and YQ, initially found by Sinai Robbins in his thesis in 1991. Then with my student, Jonali, so we also found some results on XQ and YQ. And in fact, partition theoretic interpretations can be given for those types of results. And but we never thought that those will be used in finding these matching coefficients. Okay, so we have found, and we also found 2 new results. These are 2 new results. So we developed 2 new results to prove our theorem. The theorem that connects XQ and YQ. This is the theorem connecting XQ and YQ. And these are the results. Okay. And so we actually numerically checked many other results, but we failed to find except 2. For example, here, and this is a conjecture concerning RQ and RQ14. RQ and RQ14. And there is a relation connecting ZQ and ZQ14 and HQ and HQ14 given by Ramanujan. And from that, as I told you, that we need some minus, there is a Q power something here in between. So this is a function connecting ZQ HQ. And this is another function, so say ZQ SQ, F prime say, ZQ HQ. Okay, and in between, this power of Q is negative of something or positive of something, plus minus something. What we need is that the other sign. The other sign. For example, if it is Q power say 6, if it is minus Q6, then we need actually plus Q6, formula for plus Q6. So, and that is the problem. So we could not find the corresponding formula for the other sign. And if we can find for the other sign, then we can actually try. I cannot say that we can prove it, but actually one can try to find the result on matching coefficient. That means to prove this result. But 2 things is that that result is not there. That means whether it is the other sign, the opposite sign result is not there. Secondly, we do not know how to proceed without that. Okay. So, but we have checked this for Q power Q for a very large power of Q, and we have seen that this holds. So we conjecture it. Similarly, there are more results that involves again Rogers-Ramanujan functions, but it is combination of many things. Okay, different functions. For example, here it is 5 Q3 K7. Here it is somewhat different. Okay, so here also the same thing. Some results are available for the opposite sign, but the corresponding result connecting GQ and HQ is not there. And the interesting thing is that most of the results that Ramanujan and others proved till date, those are just opposite sign of this. So we could not find what is that the positive sign or negative sign. What would be the format? What would be the formula for that? Okay. So those are put as conjectures. So this is what I wanted to say. And to prove the theorem, why we need positive, negative, etc. So you can see that to prove, for example, suppose I want to check the matching coefficients of RQ square and R square Q, and its inverse from Ramanujan's formulas for GQ and HQ, there is a formula for minus, one can find. RQ square over R square Q minus R square Q RQ square. And this is well studied, and there are many sources of this, that there is a formula for this equal to some functions of f minus q. There are some functions of f of minus q. Okay. But to prove the matching coefficient result, we want plus. Okay, we want plus. So therefore, we have to find, first we need to find the corresponding result for plus. And for that, we need to find the corresponding result connecting GQ and HQ, which the sign that is opposite to what is given in Ramanujan's formulas or others' formulas. So therefore, we developed 3 formulas for GQ and HQ. Those are new. And most of the results on Rosas-Ramanujan type, this type, can be proved by considering this type results. If coefficients are negative, then we consider plus. If coefficients are equal, then we consider the minus of something. Okay. So that was the idea. Okay, so that is this. So that is what I wanted to present. It is not a. I presented it in a very haphazard manner because this paper is written only completed very recently, so I could not actually prepare the slides very properly. But these are the theorems. Theorems I have prepared. This. In fact, Hiro helped me in writing this. Okay. Atul.
Thank you, Nayandeep, for a very nice talk. Are there any questions?
So I don't have a question, but I want to comment that I really appreciated that he did it in this way, and it wasn't. It seemed like work in progress, and he explained it on his pad. That was really nice. So I really appreciated the talk. I'm glad you didn't give a formal presentation like you. I mean, that's also good, but this was a lot of.
Okay.
So Nayandeep, I had one question. The idea, identity regarding the Goldnitz-Gordon functions was really nice, very symmetric. The S and T, the new one that you found. So that had a minus sign in between, right?
Yeah, the minus sign was already proved by somebody.
Okay.
So we proved only the other one. Okay. Method is not same, somewhat different, but I have not presented the proofs yet.
Okay. No, there was one slide in between where you said it was a new Goldnitz-Gordon.
That is new.
Yeah, that one I really liked. It was very symmetric.
Almost all identities are symmetric like that. SQTQ, okay. But the older formula that has the opposite sign.
Okay. Oh. And regarding those identities for G of Q and H of Q that you said you found, the 3 new ones.
Yeah.
So are these of new type than 40? Because you see, Ramanujan said that each of these 40 identities is a representative of something of a more general class, right? So but these do not come into those 40 classes you are seeing.
Yeah. So
that's really nice.
And another thing I want to mention that you might actually it is known that there is the first identity. If you remember the first identity of Rosas-Ramanujan relations, that is G power 11, I think, and HQ. Okay, and there is a minus sign in between. Okay, so to prove our result, we need a plus sign. Okay. And Ramanujan said that in his communication to Proceedings of London Mathematical Society that there are, as you told that these are the classes of something. Okay.
Right.
So in fact, there is only one identity of that type till date.
Okay.
And that plus identity we have found.
Okay.
Okay. But that is not as simple as the corresponding identity for the opposite sign given by Ramanujan. In Ramanujan's case, there are, I think, on the right-hand side, we have two terms, and the first term is 11q, n plus something.
Yes.
F1 power 6 divided by F5 power 6, I think. 11q plus that one. And we have found that the plus sign on the left-hand side. On the right-hand side, we have found not two, three quotients of eta functions.
Oh. So you mean to say the one where you have r raised to 5 of q minus 11 minus 1 upon r raised to 5 of q?
Yes, yes.
That has this decomposition, right?
Yeah, decomposition.
Right, yeah. Okay. So you have found that with the plus in there.
Yeah, plus sign, but unfortunately we could not use that to prove the matching coefficient result. We have used Ramanujan's famous modular equation relating RQ and RQ power 5 that is written in his first letter to Hardy. So that we have used.
The U and V one.
Yeah. Yes, U and V.
Right,
but this is a new result. Ours is a new result.
Okay. So then once you have the corresponding identity with a plus sign in between for a one where you have a minus sign, of course, then you have product representation or sum of products representation for each of those things, right?
No. Unfortunately not.
Oh, I mean, you have something like A of Q minus B of Q equal to something and A of Q plus B of Q equal to something. So
no, what I mean to say that suppose we have something plus or minus, whatever you say, on the right hand side, we'll get some Q products. Okay. And that do not vanish for all. Only for the identities that we stated and the conjecture. Apart from that, none of the other 40 identities, they vanish.
Okay.
That means you cannot say that if I find the opposite sign formula, we can find a matching coefficient. That may not be true. That may not be true. Okay.
Yeah. No, what I wanted to say was, if you get a corresponding result with the plus one, and then you add the two equations, you are getting a representation for each of those components, right?
Yes, that is correct. So that is true.
Does that give rise to any congruences or something? Like or some partition theoretic interpretation? Because you have explicit representation as sum of Q products.
Yes.
So that might be another interesting thing.
Yes, that will be interesting.
Yeah. Okay. Thank you. Is there any other question?
Can I ask a question?
Sure.
Yes.
Thank you for the talk. First, many interesting results. Actually, I have two questions. The first one is one of your results you mentioned is related to Ramanujan's modular equation of degree 7, which has combinatorial interpretation. You said parts multiple of 7 appear twice, remember?
Yes. Yeah.
So if I remember correctly, that particular result has been generalized by Warner to some identity with 3 parameters. So my question is, have you tried to get, your efficient results with respect to those generalized results with extra parameters?
Yeah, actually, we tried some of that, but not coming. The results on matching coefficients are not coming from those.
I see.
And those are already coming. So those are already stated by modular equations, already stated by Ramanujan.
Okay. And then my second question is, so for some of your results, you said there is partition theoretic interpretation for both sides, right? The coefficients, the one side and the other side is the inverse. So have you tried to prove this combinatorially?
Not yet, but what we have done is that.
Does that seem possible? I mean,
Yeah, that
opinion?
may not be impossible. That would be a very nice thing if we can find some, because you see that on the left hand side we are getting some odd or distinct or something, and on the right hand side also we are getting some Q products, and there might be some obviously some partition theoretic interpretations for that, but we have not studied yet. But what we have studied, that the coefficients, some coefficients have some, you can say that there are results on infinite families of the partition theoretic results, not the interpretation. For example, you have here for the matching coefficients, we have something alpha of twice n plus 1 is something, isn't it, on the right hand side? We can generalize that. That means alpha of, we can find generalization of alpha of some p of something. That means that sequence we can generalize. That means there will be infinitely many sequences. That we have done.
Okay. So the paper has been written up?
Yes, that has been submitted.
Are you planning to put it on archive so we can have a look?
Yeah.
Okay.
Okay. Yeah, we are planning. Yeah.
Thank you.
Okay, thank you.
Good work.
Any further questions? Okay, if not, let's unmute ourselves and clap for Nayandeep for a nice talk.